SwayamPrabha. Digital India. Educated India.
We have already derived the boundary layer equation both in differential as well as in integral form. Okay. Without going to a formal solution of these equations either in the differential form or integral form, we will consider a special case with the assumption that the solution is given to us. Okay. The solution of these equations, that as I mentioned earlier, that we would like to postpone it for the other courses, but what we would like to consider today is a situation where a solution is given. That may not be a realistic solution, but as an example solution. Okay. For a simple case where there is no pressure gradient, there is no streamwise pressure gradient. In the inviscid flow, the pressure in the x direction is constant. Pressure of course, within the boundary layer is constant, that is always, but here we are also assuming that the pressure in the x direction or the streamwise direction is also constant. It is dP dx is 0. We have seen what the form of the equation becomes in that situation, only that term dP dx becomes 0. See, this is the usual situation for a flat plate type of flow. For a flat plate, as you know that if we put a flat plate in an uniform stream, then over the flat plate in an inviscid flow there will be no change in anything and the pressure will remain constant. The velocity will not change, neither will the pressure. So, this is a situation where there is no acceleration in the inviscid stream, no deceleration, uniform velocity of the inviscid flow. So, that is the situation we would like to consider, and in that let us say the velocity profile is given. Also it is stated that the boundary layer is similar. Velocity profile is independent of x, that is at all x location the boundary layer velocity profile can be expressed in such a manner that it is same at all x location. Okay. So, this that is called a similar boundary layer. We can express in special form where the velocity profile will behave as if it is independent of x. At all x station it is the same velocity profile. You can have just only one velocity profile curve. As you can see here that, see, this is, if we plot u by u v along the x axis and say y by delta along the y axis, then at any x location we will have the same curve. That is, we can say that u by u e is a function of y by delta alone. So, now we say that we are given that we have a flat plate type of flow, no pressure gradient, and the boundary layer is similar. So, no streamwise pressure gradient, Now, before we move forward, a few words about this boundary layer thickness delta. We have earlier also said that this boundary layer thickness delta is a little bit arbitrary. It is not a very suitable parameter to define thickness. There is ambiguity how to define boundary layer thickness, because in reality there is no well defined edge where the velocity is becoming fully the inviscid flow. So, for practical uses, sometime we take it is where the velocity reaches 99.5% of the inviscid flow, sometime it takes, or some people take it is 99.75% of the inviscid flow, and so on. There is an ambiguity about it. However, it is always used as a parameter and always treated as an unknown. You need to find it. So, if we consider a similar boundary layer, the simplest possible similar boundary layer, that is what we would like to start with. It is of course unrealistic, no practical boundary layer profile are like that, but since we want to just test how to handle it, I think that will perhaps serve the purpose. What is the simplest possible then velocity profile? What will be the simplest form of this? A simplest function of y by delta. No, then that is not a boundary layer profile. If you say u by u e equal to constant, that means the velocity is remaining constant, that becomes inviscid flow. It is not a boundary layer, variation must be there, y by delta. So, that is what we will take, is a linear profile. Consider a linear velocity profile. The geometry is flat plate, the body geometry is flat plate. We would like to see that when the velocity profile is linear, what is the growth of the boundary layer, how the boundary layer grow, what is the skin friction and skin friction drag, that sort of things we would like to find. Now, if u by u e equal to y by delta, remember delta is unknown, and of course, it changes from x point to point, that is delta is a function of x, is not a constant, and usually delta increases as we move downstream, that is what is boundary layer growth. So, first find out what is delta star. What is delta star? How much is this? This is delta by 2. Okay. So, the displacement thickness is delta by 2. What is the momentum thickness? Theta. delta by 6. Okay. All right. So, what we call that momentum shape parameter, the shape parameter is how much? Delta star by theta, that is 3. How much is the skin friction coefficient? Oh, sorry, that is, this is tau wall, this is not the skin friction coefficient. Will how much is this? Nu by delta. And then CF becomes the skin friction coefficient CF okay, 2 nu by u square delta. Mu u e upon delta, yes, yes, that u e I left, and here there will be no u square, it will be simply u e. Okay. Let us write it. Now, the delta is yet unknown, we do not know what is the thickness of the boundary layer. So, how to find that? Any suggestion? Do you have any suggestion how to find delta? Because these are not complete, these are just some intermediate steps. We do not know any of these, we do not know delta, we do not know delta star, we do not know theta. H is of course known, it is a number 3, we do not even know CF, none are known to us. So, we can now use the momentum integral equation, and for, so let us use the momentum integral equation for 0 pressure gradient. The equation is then simply d theta dx equal to half CF. That term h plus 2 into theta y u e into d u e dx, that is 0, because d u e dx is 0. So, we now have d theta dx equal to and if we substitute this value, what is d theta dx? One by 6 d delta dx. Half Cf is nu by uv delta. Okay. So, what is delta now?
under root 12 mu x by u.
So, right, delta equal to under root 12. Okay, we can write it as 2 root 3. Okay, 2 root 3
Under root mu x by u. The whole expression is under root
2 root 3
mu x
nu x.
by u.
Can we express it in terms of local Reynolds number? Local Reynolds number is Reynolds number, as you know, uv into a length into nu. If we use the local length is x. So, if you use uv x by nu, that is what is Reynolds number, local Reynolds number. Express it in terms of
So 2 by mu multiplied by under root 3.
hmm?
2 by mu multiplied by under root 3.
2 by
Mu u sorry.
2 by uv 2 by uv
Under root 3 in multiplication in the whole. Under root 3
under root 3 r. So, that Reynolds number is multiplied. This we will call it r x. This
nu by u.
that nu by u is still there. Huh?
Two x into under root 3 by r x.
Otherwise, what it is 2 2x
3 by r x.
or 2 root 3x.
2x is complete, then under root 3 by r x.
No, we will put it like this 2 root 3 x
Root r x. R x.
this. Okay, let us see. Take. for granted. Now, once we have found delta, we can find the other parameters all. Once we have found delta, we can find now what is delta star, what is theta and what is even CF. Delta star you can write, delta star is delta by 2 . So, if we take yours is correct, then this is what is CF? What is CF? See what we discussed earlier from logic or from earlier solutions, that the boundary layer thickness is proportional to inverse square root of Reynolds number, that we have obtained here also. CF is 1 by root 3
under root 3 RUX.
this. In particular, if you say that delta at the trailing edge of the plate, at the trailing edge of the plate, what is delta? At the trailing edge of the plate, delta is 2 root 3 L by RE, or delta by L is 2 root 3 into 1 by remember this REX is UE x by nu and RE is UE L by nu. What will be the total skin friction? What will be the total skin friction? CF. Oh, there is 1 by L this is. How much it is coming? You can use this expression for convenience and then later on convert it to Reynolds number. How much it is? How much?
2 nu by u under root 3.
Reynolds number. In terms of Reynolds number.
Two by root 3.
2 by root 3.
Yes.
Okay.
Under root x by L R E x.
No, there will be no Rex now. After the integration, how can there be an Rex? There will be no x after the integration.
So 2 by under root 3 R E.
2 by under root 3 Re, the final answer. 2 by under root 3 Re. How much is 2 by root 3? Something must be 1 point something. How much? Can anyone say how much is 2 by root 3? How much will be 2 by root 3? One point
1.16.
1.16. Okay. So this is the total skin friction for one surface of the plate. So if the plate is immersed in a fluid, then the drag force skin friction drag on the plate is two into that quantity. So, in case we know the solution or how the velocity profile is, we can get the other answers, particularly the viscous skin friction drag. But as we mentioned earlier, that viscous skin friction drag is not the only drag. There are other contribution to drag force also. One is that the boundary layer itself modifies the pressure distribution, and the implicit pressure distribution does not give any drag force, but when you consider the boundary layer and the modified pressure distribution, that pressure distribution gives some drag force. In addition, when you consider that the body is finite in the third direction, that finite geometry also produces another drag, okay, which is known as induced drag. So, that will also be present in case, which is usually proportional to the square of lift coefficient. And then there will be one more drag which appears only in supersonic flows. So, other part of those contributions will be discussed later, not now. Now, look into these results, what you see that the boundary layer thickness increases with square root of x. Boundary layer thickness increases with square root of x. As in a zero pressure gradient flow. Now, let us see what are the fundamental differences of a boundary layer in a zero pressure gradient flow and flow with pressure gradient. This is what we consider a zero pressure gradient flow. And we would like to now consider what is likely to happen. Of course, we are not going to analyze, but just some intuitive or some logical thinking, what is going to happen to the boundary layer development or boundary layer growth when there is pressure gradient. So, let us consider growth of boundary layer with pressure gradient. To do that, let us once again consider the boundary layer equation. Only the momentum equation we would like to consider, which is we will consider steady flow. Okay. We will consider steady flow. Which as you remember is u du dx plus v du dy equal to minus 1 by rho dp e dx plus nu satisfy this bound equation at y equal to 0. This equation satisfies within the boundary layer. So, at y equal to 0 also it will satisfy. Now, satisfy it at y equal to 0. At y equal to 0, what is? We know at y equal to 0, u is 0, v is 0. So, the entire left hand side is 0. So, what we get? Okay. Now, first consider the zero pressure gradient case. The zero pressure gradient says that d 2 u dy square this is 0. Or the second derivative of velocity at y equal to 0 is 0. What we can say about the velocity profile then? What we can say about the velocity gradient or u? Velocity gradient is constant, du dy is constant? No, that is of course not. How much is the velocity gradient at, say, at the edge of the boundary layer? 0, that is known. The du dy at y equal to delta is 0. So, that constant is not possible, then that means everywhere it is 0. Then what can you say about du dy? This is only for this is y for equal to 0. On the edge of the boundary layer du dy is 0, because in the implicit flow the u is no longer changing with y. Okay. So, all the derivatives are 0 there. That is known. At the edge of the boundary layer. Du dy, derivative of du dy is 0. When does it occur? If the function is not a constant, du dy is not a constant, that we have seen.
It might be a function of x. It might be a function of x.
It might be a function of x. Or we are not considering any y x variation here, we are just simply differentiating with respect to y. At y equal to 0 will be 0. You will say that that du dy is 0 everywhere, or the velocity is constant in the boundary layer. that is of course against the concept of boundary layer. It is not 0. It would have been a fantastic situation if du dy on the at y equal to 0 would have been 0, then there would have been no skin friction drag, you know, and your aircraft could have flown without any fuel. So, du dy on the wall is not 0. When is the derivative of a function 0? If the function is not constant. Is maximum or minimum? So, du dy will have highest value at y equal to 0, largest value, and definitely it is positive, and definitely it is positive because u is 0 on the wall and then it is increasing. So, definitely du dy is positive at y equal to 0 in this case. And we can see that du dy starting from a positive value at y equal to 0, it decreases smoothly or continuously within the boundary layer.
At the maximum double derivative is negative if it is a point of maximum.
So, it is not exactly derivative because the function is not defined after that. For y equal to negative, after that the function is not defined. So, we can't do that. It is not maximum in that proportions that it will have the largest value. So, du dy, the variation of du dy will be something like this. Smoothly decreasing as y increasing. Now, consider a pressure variation where this dp dx is not 0. Let us first consider dp dx is negative, dp dx is negative. When dp dx is negative, what we will call the flow is accelerating or decelerating? If dp dx is negative, accelerating, because we have already seen dp dx is minus u du dx. Then what about dtu dy 2? What in this case? Will there be any variation from the earlier case? Remember simultaneously that u is also increasing from 0 to u v. That part also you must remember while thinking about the gradient, that u will increase from 0 to u v, from y to delta. U is increasing from 0 to delta. Since u is increasing from 0 to something at the wall, so du dy there is positive. Du di on the wall is always positive, not always, say it is positive when u is increasing. But then d2u dy2 is negative. It will also be similar to the earlier one. Similar to the zero pressure gradient case almost as far as this trend is concerned, and in either cases there will be no inflection point in the velocity profile. A decreasing function in both cases, and in both cases there is no inflection point in the velocity profile. Consider now the other case, the decelerating flow. This time there will be an increasing, but then it has to decrease again. Okay. So, then what else? du dy will change sign. Or what does it mean? The velocity profile will have an inflection point. The velocity profile will have an inflection point. Now, then what really happens in cases is that a situation comes where du dy, as you can see, the du dy on the wall in this case will be much smaller compared to the other cases. Not only that, as we move downstream, a situation will come where du dy on the wall will become 0. A du dy on the wall will become 0, and subsequently du dy near the wall will become negative. And what does it mean? That actually in that part the flow is not from the direction that we considered earlier or that we are analyzing earlier, rather it is from the other direction, that there is some back flow or the original main flow that has separated from the body. That has separated from the body like this. Let us say the flow is coming like this, and after this, instead of going like this, it has separated, and flow from this side has come like this. This is the point where that say du dy equal to 0, or it means the skin friction coefficient is 0. Now, in an airfoil type of geometry or a streamlined geometry, this separation occurs at certain angle of attack, not at 0 degree or 1 degree at that type of angle of attack, but rather of the order of 15 degree angle of attack, this separation stops. When this separation occurs, the airfoil experiences a loss of lift, the lift coefficient started decreasing, and if the separation is say further here somewhere ahead, then the lift will become so small that aircraft may not be able to fly, rather fall down like a stone, known as stall, which is because of this boundary layer separation. However, as you will be knowing that, see immediately that whenever there is a positive pressure gradient, it does not mean that the flow has to separate. As you said that a positive pressure gradient, which is known as adverse pressure gradient, that the pressure is increasing downstream, that point of inflection is obvious, it will be there, but later on you will see or you will learn that if the velocity profile has a point of inflection, then the flow is highly unstable. you might have heard of something called as stability, instability. Okay. The mathematical equations which represent some physical system, they become unstable. Anyway, we will not discuss that, but if there is a point of inflection in the velocity profile, then that flow is likely to be unstable. And what actually happens, that before this separation occurs, the flow changes its status. What essentially we are discussing are called laminar flow, where layer slides over layer, where fluid layer slides over fluid layer, this type of smooth regular flow. Instead, it becomes something called turbulent, and a turbulent flow can withstand this adverse pressure gradient much better than a laminar flow. So, when the flow becomes turbulent, then the separation perhaps will not occur where it was supposed to occur in a laminar flow, rather it will move downstream. See, this process of separation can also be very easily understood. See, when the pressure is increasing downstream, the flow is moving against that rising pressure. It is like, think of yourself, you are trying to climb a hill, as you go up upper, you feel tired, and if the hill is too high, you might not have the sufficient energy to go to the top. Okay. Similarly, as the flow moves against this rising pressure, it consumes its energy, the kinetic energy. Okay. It uses the kinetic energy to overcome that rising pressure. So, if the kinetic energy is not sufficient, it will not be able to move against that adverse pressure. After some distance, it will lose all its kinetic energy, and then it will be blown away from flow from the other direction. It is being blown away.